Okay, the next is the electrophilic reactions. But we first need to understand what an electrophile is. So the electrophiles, as the name says, is the electron files. Files mean loving. So they're electron loving, so they need electrons. So these are the substances that can accept a pair of electrons because they are a bit short of electrons, so that's why they are attracted to electrons. Examples of electrophiles include positively charged ions, for example hydrogen ion and NO2 plus ion. Similarly, the polar molecules also behave as electrophiles. For example, we have the hydrogen bromide. Because of the difference in the electronegativity of the hydrogen and bromine, the molecule becomes polarized. Hydrogen gets partial positive charge and bromine gets partial negative charge. So it is a partial positive atom that is attracted to the electron density. Now let's move on to the first type of the electrophilic reactions called electrophilic addition reactions. So we'll be talking about electrophilic addition reactions of alkenes. And you must be wondering why alkenes? Because alkenes have carbon-carbon double bond, and double bond means they have more electron density, and that's why they are more at risk of electrophilic attacks. So we will discuss three different types of reactions. The first is the reaction of alkenes with polar electrophiles. The second would be reaction of alkenes with neutral electrophiles, and the third one is reactions of unsymmetrical alkenes with polar electrophiles. So just keep in mind both these alkenes will be symmetrical. So let's start with the first type, reactions of alkenes with polar electrophile. We first look at the general reaction mechanism. So here we have an alkene, CH2 double bond CH2, and then we have the polar electrophile AB, where the A side is a partial positive and the B is the partial negative side. So A will behave as an electrophile and will attack the carbon-carbon double bond and will break one of the bonds and will make a bond with one of these carbons. So here is the A. So we already had two hydrogen and now A has become a part of the carbon. So A has made a bond with the carbon, while this carbon is now carrying a positive charge because it's lacking one bond. It needs to make a bond. Remember, you have to turn an arrow from the double bond to the electrophile. It's taking a pair of electron and making a bond with the carbon. Similarly, you have to put a curly arrow from this bond to B because A is now no more part of B. So the pair of electrons that was shared between A and B, that will move to the B, and B will become B negative, and here is a pair of electrons is carrying. This carbon needs a pair of electrons to complete its 4 bonds, while this B is carrying a pair of electrons. So they are perfect match. So B will give its pair of electrons to the carbon and make a bond with the carbon. So you have to put a curly arrow from this pair of electrons to the carbon. That means that B is giving is a pair of electrons to the carbon and make a bond with the carbon. And this is how it looks like. So we end up with CH2A, CH2B. Now it should be very clear to you why this is called the addition reaction, because the original polar electrophile AB has added itself to the molecule and is now part of the molecule. Okay, now let's look at the real example. So the first example is between butene and hydrogen bromide, which makes 2-bromobutane. So this is butene, and here on the bottom we have the hydrogen bromide. Okay, so to write its mechanism, put a curly arrow from this double bond between carbon-carbon to the electrophile, which is hydrogen. So that means hydrogen will make a bond with this carbon and will break the bond with the bromine. So bromine will take the pair of electrons that was shared between hydrogen and bromine and become B negative. So as you can see here, so we already had the CH3CH, which is here, CH3CH, and this hydrogen has made a bond with the carbon. And at the same time, we will show that this carbon is now carrying positive charge, and this is the bromine carrying lone pair of electron. So bromine will give its lone pair of electron to the carbon atom and make a bond with this carbon. And this is what we get at the end. This molecule is called 2-bromobutane. So overall, alkene has been converted into an alkane, and HBr has added itself to the molecule. Okay, now let's have a look at another example. So again, we have the same molecule, butene, but we have a different electrophile, and it's sulfuric acid or H2SO4. That will make 2-butyl hydrogen sulfate. Okay, so here is our butene, and on the bottom we have the sulfuric acid. So H2, one hydrogen, second hydrogen, SO4. So we have the sulfur in the middle and 4 oxygen on the outside. So the sulfur has a double bond with 2 of the oxygen and single bond with 2 of the remaining oxygen. And each of these oxygen is attached to a hydrogen. Because of the difference in the electronegativity of the hydrogen and hydrogen gets a partial positive charge and oxygen gets a partial negative charge. So that makes the hydrogen an electrophile. So again, you put an arrow from the double bond to the hydrogen. So hydrogen will make a bond with the carbon, and at the same time the bond between the hydrogen and oxygen will be broken. So the pair of electrons will move to the oxygen and oxygen will become all negative. So this is the hydrogen which has made bond with the carbon, and carbon is now carrying a positive charge because it lost its covalent bond. So this oxygen will give this lone pair of electrons to the carbon and make a bond with the carbon. And this is what you get at the end. So there's a bond between the oxygen and the carbon. So sulfuric acid has actually become a part of this molecule, and that molecule is called 2-butyl hydrogen sulfate. So again, we have an alkene being converted into an alkane because of the electrophilic addition reaction. Okay, so now let's move on to the second type of reaction, which is the reaction of alkenes with neutral electrophiles. Now that will be a bit confusing for you to say a neutral electrophile, because if it is neutral, then how is it an electrophile? To understand this, let's have a look at this little animation. So let's say we have this alkene and it's got double bond. Here we have our neutral electrophile. It's neutral because it had the same atoms, so overall there is no partial positive or partial negative charges. However, when this molecule comes closer to the alkene has a double bond, which is the high electron density area. And these electrons push the electron cloud on the molecule, and the electron cloud is actually pushed to this side, giving the opposite side partial negative charge while giving this side partial positive charge. This is how this neutral electrophile becomes temporarily polarized. Once it becomes polarized, it will behave like a polar electrophile, and the rest of the reaction would be the same as for the polar electrophile. So let's look at one example. So we have again the but2ene, and this time we have a neutral electrophile, which is bromine, and that will make 2,3-dibromobutane. So let's have a look and see how this mechanism takes place. So here we have our but2ene molecule. On the bottom we have our bromine molecule. Because of the push of the electron, the bromine atom away from the carbon-carbon double bond gets partial negative charge, while the bromine atom close to the double bond gets partial positive charge, and it starts to behave as a polar electrophile. So again, you have to put an arrow from the carbon-carbon double bond to the positive bromine atom. So this bromine will make a bond with this carbon, while at the same time the bond between the bromine will be broken, and this bromine will take the pair of electron and become bromine negative. So here we have the bromine, which has now made a bond with the carbon, and here the carbon, which has now got the positive charge. Bromine will then give its pair of electron to the carbon and make a bond with the carbon atom, and the resulting molecule would be 2,3-dibromobutane. So overall, the bromine is now becoming a part of the alkene. So that means bromine itself doesn't exist. So we can use this property to test for the presence of alkene. So if you have a compound which is suspected alkene, what you do to test, you add a bromine water, which is an orange color. If there is an alkene, bromine will react with the alkene and will convert it into an alkane, and the bromine water will become decolorized. Now let's move on to our final reaction, which is the reaction of unsymmetrical alkenes with polar electrophiles. So far we have talked about the alkenes which are symmetrical, but if you have unsymmetrical alkenes, they will behave differently. Let's have a look at an example. This time we have but1ene, and it's going to react with the hydrogen bromide. This time we're not getting one product, we're getting two different products. So one of them will in more quantity and will be called the major product, while the other one is called the minor product. For example, in this case we will get 2-bromobutane, which will be the major product, while 1-bromobutane will be the minor product. Now let's see how this mechanism works. So here we have but1ene, and on the bottom we have hydrogen bromide. So the hydrogen side is carrying the partial positive charge and will behave as an electrophile. So it will make a bond with the carbon, while at the same time the bond between the hydrogen and bromine will be broken, and a pair of electrons will be taken by the bromine. But there's a slight confusion here. We know that hydrogen is going to make a bond with the carbon, but if you look at the molecule, that's an unsymmetrical molecule. So both these carbons are different. This carbon is attached to two hydrogen, while this carbon is attached to a methyl group. So now the question is, the hydrogen will make bond with which carbon, with this carbon or with this carbon? So in reality, hydrogen will make a bond with this carbon, and it will also make a bond with this carbon. So that's why we'll get two different products. Let's have a look at the first option, which is the major product. So hydrogen make bond with this carbon, and bromine will make bond with this carbon, called the secondary carbocation, because this is attached to two more carbons, so that's why it's called the secondary carbocation. So bromine will make a bond with this carbon, and the end product would be 2-bromobutane, and that would be the major product. The second product would be 1-bromobutane. So in that case, hydrogen will make bond with this carbon, and there we have that hydrogen. And this carbon will carry the positive charge, and it will be called the primary carbocation because it's only attached to one more carbon. And bromine will make a bond with this carbon, and the end product will be 1-bromobutane, and that will be the minor product. So the rule is that secondary carbocation has a first preference over the primary carbocation. Similarly, if there's a tertiary carbocation, that will have a preference over the secondary carbocation. So in this case, the major product would be 2-bromobutane, while the minor product would be 1-bromobutane. Okay, so now let's move on to the electrophilic substitution reactions. And we're going to consider the example of the benzene, because benzene doesn't like the addition reaction, but it's like the substitution reaction, because that keeps integrity of the benzene ring. We're going to consider two different examples. So one is the nitration of benzene, and the second is the acylation of the benzene. So let's start with the nitration of the benzene, which means substitution of the nitro group. So this is how the reaction mechanism looks like. So benzene is nitrated into nitrobenzene, and for that it needs nitric acid and concentrated sulfuric acid and 50 degrees centigrade temperature. To make the nitrobenzene, benzene needs to have a nitro group. So we first need to have a look at how the nitro group is formed. So our electrophile would be the nitronium ion NO2+. This nitronium ion is produced as a result of the reaction between the sulfuric acid and the nitric acid, which takes place in several steps. So sulfuric acid reacts with nitric acid to initially make the bisulfate and H2NO3+. H2NO3+ is then broken down into nitronium ion and water. Sulfuric acid then reacts with the water to make bisulfate ion and hydronium ion. So overall, nitric acid reacts with the sulfuric acid to make the nitronium ion plus bisulfate ions plus hydronium ions. So if you look at the reaction mechanism, so here we have the benzene ring. The circle represents the delocalized electrons of the benzene. So nitronium ion takes these delocalized electrons and makes a bond with the benzene. So that's why we have to put a curly arrow from the delocalized electrons to the nitronium ion. But that causes the delocalized electron ring to be broken down. And for the stability of the benzene must recover these delocalized electrons to complete its ring. The benzene takes these electrons by breaking this bond with the hydrogen. So it takes the electrons that was shared between the carbon and the hydrogen to complete its ring. So at the end we get nitrobenzene and hydrogen ion. So it is this hydrogen ion which combines with the bisulfate ion to make the sulfuric acid, because sulfuric acid is regenerated. So that's why the sulfuric acid acts as a catalyst. Okay, so now let's look at the acylation of the benzene. So acylation is the substitution of the acyl group. So we're going to look at this example when benzene reacts with ethanol chloride to make phenylethanol. So basically this chlorine is removed and all this acyl group is substituted onto the benzene. So the electrophile in this case will be the acylium ion CH3C plus double bond O. And this is produced as a result of the reaction of ethanol chloride with the AlCl3, which produces the acylium ion. So this is the overall mechanism. So here the carbon of the acylium ion acts as the electrophile, and it takes the delocalized electrons and make a bond with the benzene. But that breaks the ring, and again to reform its ring, benzene breaks a bond with the hydrogen, takes its electron to complete its ring, which results in the substitution of the acylium ion with the benzene, and we get phenylethanol plus a hydrogen ion. It is this hydrogen ion which combines with AlCl4 to regenerate AlCl3.